So my name is Max Shtein. I'm in the Material Science and Engineering Department, and it is my great pleasure to introduce our next speaker. When I was asked to introduce our next speaker, I had a chat with Steve, and we agreed that he'll shorten his presentation to 5 to 10 minutes today because we need a lot of time to list his accomplishments. Well, so but aside, I will list his accomplishments because I think it's very important, but I want to go through a couple of slides first to kind of make sure that we understand what this means in terms of a paradigm shift. So this is Achilles Dilemma. You might remember it from your ancient Greek mythology or from English class, because there are a ton of essays you could buy for $1.50 that talk about Achilles Dilemma. I carry two sorts of destiny toward the day of my death. Either if I stay here and fight beside the city of the Trojans, my return home is gone, but my glory shall be everlasting. But if I return home to the beloved land of my fathers, the excellence of my glory is gone, but there will be a long life left for me, and my end in death will not come to me quickly. This is a dilemma because there are basically two choices here that he's deciding between. So he can stay and fight and achieve glory. In the old days, that's, you achieve glory in battle, and chances are that you die, or you enjoy a long life, but nobody knows about you. Okay, and that's a dilemma, and it's commonly known as a trade-off. Also known as opportunity cost. That's a word that term Steve likes to use a lot, and it's actually true. Engineers in industry call it Pareto efficiency. Economists know about it also. Commonly known as you can't have your cake and eat it too. Now we can draw a diagram of Achilles Dilemma using the Pareto efficiency plot, right? And that maps kind of like that. The choices. And the idea here is that you have this conflicting desires diagram that's actually pretty universal for a lot of the challenges that we face. And the question is, can we have both? What's interesting is that we can diagram ancient Greek mythology using this concept here. So Eumaeus is a character who's a swineherd. He's a commoner. He's engaged in a normal life, which is measured in a pair of numbers. Okay, so and he scores pretty high in terms of years, low in terms of glory. We have Achilles. He's a war hero. He's engaged in a life of mortal combat, and that's measured in a low number of years and a large number of glory, right? So what we're doing here is we're pulling ourselves up into kind of broader categories, and when you do that appropriately, there's actually a mathematical theorem that says, called category theory, that says that you should be able to come up with a solution that gives you the best of both worlds. And so the broader category here is that they're all persons, and they lead a life, and the life is measured in a pair of numbers, but they don't have to be necessarily those specific numbers. So it kind of maps like this. So what happens then is that Homer, our poet, actually invents something. He invents something new, and this innovation in the realm of life and storytelling about life, he calls it polytropos. Tell me, muse of a man of many ways. So the man of many ways. And so you have Odyssey as kind of a theater of play in which Odysseus kind of enacts all these different things. And he's a man of many ways. He's able to do these things. He also assembles a team of people that's able to do these things very effectively. And the result is that he actually lives a very long life and achieves a lot of glory. And so I think you probably know what I'm getting at. The deal here is that Steve is a member of the National Academy of Sciences and the National Academy of Engineering. He has, I believe, an H-index of about 145 or 150, something like, depending on whether you include the patents or not. But he also likes to talk about impact versus impact factor. And he's got a paper that has maybe something like 40 citations, which is on the low end for Steve, which happens to be about a technology which is in pretty much every telecommunications, high-speed telecommunications switch. So every time you pick up a phone and make a call, one of those devices is activated. You can now go out and buy an Apple Watch, or soon to be the iPhone X, or any Samsung smartphone that you buy. It's going to have OLED technology in it. And that's another one of these technologies that Steve developed that, largely thanks to his efforts, is now in commercial production and is a multi-billion-a-year market. Now, at one of recent events, sort of honoring Steve was, I think, a distinguished university innovator and distinguished university professor lectures. After he gave his lecture, somebody from the audience asked, "Steve, how do you do all this?" Well, when they asked Yitzhak Perlman, how is it that he can play the violin so well, he said, well, it's actually fairly easy. You just have to put your fingers in the right places at the right time. And I think that's as best as Steve can explain it, I think. But it's been a great honor to work with Steve Forrest over the years, be his student in his group back at Princeton, and it's certainly a great pleasure to introduce him for his lecture at this symposium. Steve, go ahead.
Thanks, Max. Never been compared to Greek mythology before, but I'll take it. I did say, you know, he had that glory in years, and then he told me that he gave me this thing for a clicker advance, and he said it might die before you're done, and I said, well, so might I. So, so we'll see what happens. Let's see, I'm kind of doing this because it's not appearing on my screen, so we'll just try that. It'll probably work. Okay. So today I'm going to give you a brief excursion through my favorite world these days, organic electronics, and talk about two problems and the materials challenges behind them. The two problems that I've been really focused on have been OLEDs, which there are still magnificent challenges in front of us, but also organic solar cells. So just to bring you all up to speed with one view graph, this is my world. It's the world of organic excitonic materials, as we call them, and they're very common. They're everywhere in this room today because we're all wearing dyes on our clothing, and those are monomers typically. Of course, there's plastics all over the room. Those are polymers. Very good electronic materials in both cases. And then there's biological materials, which also turn out to be very good electronic materials. As I like to explain to my students, we are simply machines that are pretty highly wired up. We're all working on electricity. And there's little things like that keep us going. The world that I'm mostly interested in, though, are the ones of monomers and polymers, and particularly the single unit materials monomers. So this is a very busy view graph, but I just thought it would be kind of fun. I use this in my course. I've shortened it down a wee bit, but I was going through and trying to figure out whatever happened in the world of organic electronics. First of all, we're very familiar with silicon electronics. We think that that's where the world started. In fact, organic electronics started very early, really before, I think, inorganic electronics. It started somewhere in the 1920s. But the most important, I think, event that happened in this field was in 1950 when Hiro Inoguchi discovered organics could be good semiconductors. And I think that was a pivotal event. I think he's much under-recognized, but so be it. Then there's a whole bunch of things that happened, but you'll notice I divided up my graph into two sections, and you don't have to pay much attention to all the detail. But there was an era, what I call, of organic science and discovery, and then that was followed by the era of organic electronics. What happened? Well, two papers by one guy. It was Ching Tang at Kodak in, I think, 1986, who announced a organic photovoltaic cell, a very simple little paper in applied physics letters that showed a junction. It was, and showed a rectifying characteristic. And then 1 year later, he, with Steve Van Slyke at Kodak, introduced the first OLED. And that just completely flipped everybody's emphasis. So before that, spectacular science was being done. The Nobel Prize went to Alan Heeger and Shirakawa and McDermott in, I think, that's when he did it, was 1977. The Nobel Prize was in 1980 or something for doping semiconductors, which is, of course, we like semiconductors to be doped because we can tailor their properties. But before that period, people were kind of fooling around with this stuff and doing some really wonderful science, Forster and so on before that, before this chart. But after that, everybody started concentrating on devices. There was a there all of a sudden, and the field exploded. And with the explosion, of course, we had our frauds. Jan-Henrik Schern, and you can't really talk about this timeline without him, but that was such an enormous fraud. If anybody's familiar with this history, it's the largest fraud ever in physics. It would have sunk any normal technology or any normal field. But because there was so much momentum now, and it was real, with the advent of the OLED, that it just powered right on by. It was exciting, but a footnote. So let me talk first about that initial innovation. It was a very simple device. It consisted of a hole transport layer, so it has glass, a transparent conducting oxide. On top of that is a hole conducting medium, and then on top of that, a thin layer of an electron conducting and luminescent medium, ALQ. This whole thing stood about 100 nanometers thick, put on a cathode on one side, and bang, he was done. Out came green light. That's the electroluminescence spectrum, and the PL spectrum is basically the same thing. It's the wonder of organics that the individual molecular properties transform into the solid, almost intact and untouched. And these were basically, Kodak was a big chemical company. These are basically dye compounds, common materials. This one was very close. This was not actually the diamine that he used in his device, but it was very close to what you would use in xerography. So this was a 1% device. It got a couple Japanese companies who were really on the edges of the display industry interested, but at 1%, there wasn't a lot that you could do with it. And then another nice advance came along, and this was actually pioneered by my student, Mark Baldo, who's a professor at MIT and a huge competitor for students from Michigan, I might add, Mark Thompson at USC, and myself, and we came up with a very simple fix to the efficiency problem. It's a very simple quantum mechanical trick. So in the Tang device, basically you excite the molecule, you inject an electron, and you inject a hole from the two opposite contacts. The electron goes up into the upper state. The hole is the missing electron in the lower state, and this luminesces. Boom, you get light out. That's the process of fluorescence. It takes a spin antisymmetric state, and therefore, during this process, you just have a simple spin-allowed transition. Unfortunately, when you inject charge, they don't know what the spin of the other charge is. So one goes in as a singlet. You've lost all your efficiency. You get 1 out of 4. The rest go in as these spin symmetric states called triplets. So spin up, spin up, spin up, spin down, and then the symmetric combination of spin up, spin down. Those are non-radiative. So by putting a metal, a heavy metal in the center of the molecule, you create something called spin-orbit coupling. It violates this quantum mechanical selection rule, and all of these become radiative, and this guy immediately transfers over, and it also becomes radiative. Now you have 100% efficiency. And this was interesting, because, and this is what powered up the industry quite literally, because now you had a device that you could carry around in your pocket that was much more efficient than LCDs, and it was actually 100% efficient. So the industry got involved, and they started making, you just basically change the spaghetti around the metal. These are all iridium complexes. You can do this with osmium or platinum or so on. But by changing the ligands, you can go from the deep red all the way to the green and all the way to the deep blue. And this whole chart is populated as a chromaticity chart, which basically assigns 2 coordinates to every color, which is one of the things that always has fascinated me, that we can turn a biological sense into 2 coordinates. I don't know, the whole thing about vision has kind of hooked in my brain. And we get very deep color coordinate, very large gamut. So you can get any color that's surrounded by pixels. Let's say in your display you have a red, green, and blue pixel element. And as long as you're down in these corners and up here, you can access any color within the triangle by simply mixing the intensity, the relative intensity of the 3 colors. Now the greens are up in here, and so these are really beautiful displays. I encourage everybody to buy them at all times. And you can get whites. So this created an industry, and this is where the industry is today. And I know this is a scientific talk, but one of the things that really excites me is that this is a marker that things that we're doing are getting into people's lives. They're changing their lives. And there are a lot of lives out there that are getting changed. If you look at 2017, the OLED display industry, sorry for the blur, it's about $21 billion this year. It's got a compound annual growth rate of something like 50% right now. So at $20 billion, that is approximately 25% of all displays made. But in fact, it's today 50% of all handheld devices. So all of your, so 50% of cell phones have OLED displays, and the iPhone X. I know there's a lot of very sad Apple consumers in this room. You know you have to wait so long for them to do the obvious. But now the iPhone X has OLED displays, but Samsung has known all along. And you can get TVs too. And if you go to Best Buy, you see these glorious OLED TVs. I don't know how many of these things have been sold. I do know that they make 1.5 million a day at Samsung alone. That's 1/3 of the display, the display market. If you think about that, you realize that Samsung is simply a logistics company. How do you get 1.5 million cell phones into trucks, or off the assembly line, into trucks, into stores, into people's pockets at the rate of 1.5 million a day? It's inconceivable to me. And it's, because it's 100% efficient, white lighting, it's still too expensive, but it's very pleasant to look at, and you can do things like windows that change from illumination sources to transparency. And these are various architectural versions of this. And you can make it flexible. I like this one. This is several years old now, but it's LG's 55-inch TV that you can roll up. And if you have a Samsung cell phone, like a Galaxy 6 Edge, it has a flexible, transparent, flexible display inside it, pushed up against the window. But there's lots of challenges, and that's what I want to talk about today. And then I'll talk later on about some really exciting developments in organic photovoltaics. So as soon as students and actually, unfortunately, other researchers see a big industry like that, they lose interest, because Samsung or LG or somebody, BOE, they're all doing it. It's fully developed. And actually, my first proposal in this topic to National Science Foundation was, I think, in 1994. And I got a call. This is when program managers at National Science Foundation actually talked to researchers. And I got a call and said, you know, Steve, your proposal got really good reviews. But unfortunately, one of the reviewers, there's always one, you'll always find them, one of the reviewers said, Kodak has done everything. By the way, that development of phosphorescence was in the year 2000. Kodak had done theirs in 1986 or 87. It's industry now. There's nothing left for researchers. And it was Al Harvey, and I said to Al, I remember I was riding in a car down the New Jersey Turnpike, my favorite place on earth. And I said, Al, do you fund anything in silicon? And he said, yes. I says, hasn't everything been done in silicon already? He said, that's a good argument. I'll use that with my director. And so he funded us, and there's big challenges still. So it really comes down to materials. And materials, in my belief, and it's a very strong belief I have learned throughout my career, I wasn't born with this, because I'm really a physicist by trade in many respects, or by training, is that the guy who has the new materials, and I also, that, by the way, guy is a genderless term. But the person who has the new materials and the new growth technology rules the world for a long time to come. Because it takes people forever to catch up with you. They just don't want to build that new machine to grow that film. They don't want to play around with that new material. They're so slow. So as soon as you get a new material and you have a new growth technology, you just can run with it. And this is the foundation of all of our technologies, as it turns out. And we saw that with, I think, with your talk, starting with the Stone Age. And in organics, it's always purity, and it's stability and functionality. And if you don't have purity, I can tell you in an electronic device or an optoelectronic device, without purity, you don't have a device. You can make things in the lab and you can publish nice papers, but as Max says, there's no impact. They have to work day after day with reliability, with predictable performance. So if it isn't absolutely pure, forget about it. And I can tell you that Samsung and LG and all these guys in organics are working every day to make them more pure. And so that brings us to the issue of, well, should it be small molecules or polymers? Now, I have a point of view here, which is that it has to be small molecules, and of course, the industry has borne that out. And the reason is because the way we purify things is we select by molecular weight. And if you have something that has uncertain molecular weight, which is a polymer, then you can't select it. And then you're also putting it down with solutions and so on. You can't always get rid of the solutions. I think that's a rather minor problem. It's really the selection of that material. Small molecules have a well-defined molecular weight. Cost and yield. I'll talk a little bit about that, so I won't belabor it here. Getting all the light out. Unfortunately, we have 100% internal quantum efficiency for most colors. 80% is trapped into the device. I don't have time to talk about this, but it's a wonderful photonics problem. We're now getting up to about 70% of the light out in our lab. And the lifetime of the blues, and I'll talk about that. The blues are gorgeous, but they give you the blues when you talk about lifetime. And I won't talk about electrically pumped organic lasing, but I feel there's another big opportunity now for looking at organic devices under very high energy environments. So that's one of the things you have in a laser. So this is the dream, and this is, now I'm going to talk a little bit about growth and processing. The dream is, let's make, organics are dyes. They're put down any which way, and they're kind of cheap molecules. Why can't we make electronics on demand by growing it by the mile rather than by the batch? One wafer at a time, one 300 millimeter wafer at a time. We're making big devices. They're solar cells, they're displays, they're lighting. We look at them. They have to be human scale. There's an irreducible size to them. Why can't we print them like newspapers? So these are the fabrication processes that have been developed. I don't want you to look at a whole lot of this. There's too much detail here. But the big picture message is that a lot of things have been developed. Today, all the displays are made by vacuum thermal evaporation. In my lab, and Max was certainly a real pioneer in this, was we came up with this process which was very much like hydride transport vapor phase epitaxy that we'd use for example, indium phosphide growth. And it basically takes a gas, a hot gas, and it evaporates the material not into vacuum, but into a gas. And I'll show you why you want to do that. And that led to another technology, a printing technology, that is practiced both in Max's and my lab, which is organic vapor jet printing, where we can now pattern at the same time as deposit. So this is OVPD. Basically, you take, instead of just evaporating a molecule into vacuum and have it ballistically transport to a substrate, we evaporate into a flowing inert gas stream, in this case, nitrogen. And then somewhere downstream, this is a hot walled reactor. It's very simple. We have a cold substrate, and everything that lands on that substrate sticks. Why do we like this? Because unlike vacuum deposition, the gas is saturated with organics. So it's basically an equilibrium process. You don't have to worry about this exponential increase in rate of transport, which you have in, with temperature, that you have in VTE, because all you have to do is turn up the mass flow. So that's simple. And it's very efficient as well. Because you have a hot wall, nothing sticks on the surface of the vacuum chamber. This stuff, you know, if you have it and you're producing 1.5 million displays a day, you have a lot of stuff getting stuck on the walls of the vacuum chamber, which means it's dusty in there. So you have to keep cleaning it. So this is absolutely clean forever, because nothing sticks there. And then you just have it stick over here on the substrate. Now, what does this buy you? Sounds clever, I guess, but you know, if it's not good for anything, it isn't good for anything. This is what it does. It controls morphology. These are big molecules, and you know, we heard this morning Professor Glotzer talk about assemblies of materials and controlling morphologies, et cetera, at the sort of the atomic level, or the kind of the little thing level. Well, these things are little things. They're molecules, and they have shape to them. So by basically changing the gas flow and the temperature, this is two axes. I'm not going to show all of them because I don't have time. But as you move toward a lower evaporation temperature, you evaporate less into the gas stream. And if you change the substrate temperature and increase it, when things hit the substrate, they can organize into their crystal structure. So you get crystalline material in this corner and amorphous material in this corner. And you have absolutely precise ability to control nanostructure. This technology, too, has been introduced into production lines. It's probably more useful for things like solar cells than it is for OLEDs, but we use it continually for OLEDs in any rate. And as I sometimes call this to my students, OVPD is the gift that just keeps on giving. Every time you grow something by OVPD, it always comes out somehow better than by vacuum. And nobody else seems to be out there doing it. It's so simple, you know. There are a few labs that are using it, not in production. Those are built by a large manufacturing company, but in academic lab they're not using it. So then, while we were really investigating the thermodynamics of OVPD, Max was my student at the time, and he suggested, why can't we focus the material? That was actually, I think, Max and Peter Pumans together worked on this. Why can't we focus the material and draw the stuff and pattern while like an inkjet printer? And the concept is, again, rather simple. You just take your material, you blow hot nitrogen gas and volatilize it. You bring in another line for just gas dilution, and then you translate the substrate, and voila, you make all kinds of devices. Well, it's easy in concept. It's always rather difficult to do these things. But we found some really exciting things early days. One is that as you grew, it's very directional. So this is the nozzle, and the heavy molecules kind of get blown off a little bit sideways by the exiting gas, the nitrogen. And this is pentacene. And on each side of the nozzle, you can see the crystallites grow in toward the growth direction. So that was rather fun. These were crude days when we were using hollow optical fibers for nozzles. You do what you can do. Since then, we have used the ability here at LNF to make MEMS devices. So I had a student, Greg McGraw, who made arrays of nozzles and see how far we could really push this thing. This just shows, I don't know if this is an OLED or a fluorescent image of what OLEDs would look like. I think this is OLEDs from the implication of this view graph. We've done them both. We've made multicolor and so on. And you can get resolutions down to 1 micron on these things. The fascinating thing is that Max and I are now, I guess, reimagining this for this technology for printing human heart tissue. That's another talk entirely. But it's once you start growing, you can grow just about anything, including heart repair. We'll see. NSF is investing, so it must be right. So let me talk about really one of the major challenges. And Mark Baldo was at a conference. He doesn't have a big dog in this fight, but he was the one, because he's moved on to other things, but he said that arguably one of the most important, or the most important problem in organic electronics today, and certainly the one that has the highest value to people, is to solve the problem of blue lifetime. So if you have a display, you have 2 phosphors in it, red and green, and the blue phosphor is replaced by a fluorescent material. So it has a limited efficiency by comparison. So it's dragging the efficiency of the entire display down. This display is still great in terms of efficiency, but it could be so much better. And this has turned out to be one of the hardest problems as well, not just the highest value. So if you look at the lifetime of fluorescent materials, you'll notice that red and green, they're good, 200,000 hours or so. The blue is pretty miserable at 11,000 hours. But now come over to phosphors. These are just pulled off the web, so I think they're much longer on this side now because people have worked so hard on this. They're in the millions of hours. But the red and the green, for very good physics reasons, have longer lifetimes than fluorescence. But the blue is a disaster, so you can't use it. But if you have a red phosphorescent OLED and replace just the red fluorophore with a red phosphor, you reduce the power consumption by 25%, do a red plus a green, which is where your displays are today, you're down about 50%, and if you replace the blue with a blue phosphorescent device, you're down 75%. So this is very valuable from battery life perspective and so on. And we work with Mark Thompson's group on some really nice devices. This just shows 2 isomers of a blue phosphor, and you can see just by changing kind of the organization of this thing, that is the organization of the ligands, whether they're in a facial or a meridional orientation with respect to each other, you go from a lighter blue. The real color is on the mat here. This is all scattered light, and the device is actually facing away from you. You get a little lighter blue than here. So this is kind of the magic of organics. You just change a few. This is the exact same molecular formula. So it's beautiful, but it's short-lived. Okay, they're cute you got to take your pictures quick, do your data, send it off to Nature Materials. They don't care about impact, only impact factor. And off you are. Off you go. I don't want to keep going on that. Okay. So after the demonstration of the first blue phosphorescent OLED, 8 years later, labs had taken this problem up all around the world. Really hundreds, perhaps 1,000 or so researchers, chemists, had struggled with this problem and made no impact whatsoever. So I went to my student, Chris Giebink, and I said, it's time for the physicists to move in on this one, because the chemists aren't surviving, aren't doing this. And we said, let's just come up with a simple physics model for what the degradation mechanisms might be, and perhaps that'll give guidance to the chemists to help them solve this problem from a chemistry perspective. It's obviously you have to deal with the chemistry, but you also have to deal with the physics, because we knew all those smart chemists and some not so smart chemists weren't having any success. So the idea is a very simple one, and probably if you take Electrical Engineering 320, you'll get some of this. You put in a defect. So we just thought, well, we have a host, which is the charge carrier, and we have a guest, which is our luminescent material. And if we just run enough charge in this thing for long enough, the holes come in here, the electrons come in here, we get an exciton on the guest, a defect forms. We have no idea what that defect is, but it's a mid-gap state. So every time now I have a guest excitation, it just non-radiatively recombines. So now you think, well, it must be energy driven. So now we're going toward the chemistry perspective. What's happening? Well, we know that reds are mostly have a longer lifetime than greens, have a longer lifetime than blue. So it's energy. Again, we're just physicists. We can claim ignorance on every other topic. And so if we look at, for example, a typical host material, MCBP, you look at all the bond energies. This only has carbon, hydrogen, and nitrogen, but these are all the kind of bond energies you would find in a molecule. And, well, if you look at red light, you've got a photon, which is 2 electron volts, green 2.3, and blue 2.9. There doesn't seem to be enough energy around to kill anything. Well, maybe nitrogen, but who'd be foolish enough to put a nitrogen-nitrogen bond in their molecules? A physicist is the answer. But we don't have any. So really, there's just not enough energy around to kill molecules, or is there? And this was really the Giebink model. And it's an Auger process. You have an excited state on one molecule. These are just energy level diagrams, as you use in organics. And you have a second nearby excited state in an adjacent molecule. And they collide. This gives up its energy non-radiatively. This one comes up here. And it gets into what's called a pre-dissociative state and breaks apart. And now I've got double the energy. I'm in good shape. I can break anything. I've got 2.9 volts for a blue exciton. I got an electron, which is about 3.3 volts. We got more than 6 volts. There's nothing in there that can withstand it. Of course, then it should just die as soon as you turn it on. They live much longer than that, which means that not every process ends up like this. Very briefly, one way you can solve this problem is to spread out in the emission zone. We have a dopant and we have a host, and the dopant these blue phosphors carry holes, and the host, MCBP, carries electrons. Basically, everything piles up at the electron transport layer interface, and so you have this high density, this soup of excitons and electrons, and that's what's killing it. So let's just grade this dopant down so it makes it harder and harder for the holes, which transport easier than electrons, to get over to this side. So they kind of smear out the exciton density. And after, wow, 14 years or something since the demonstration of the first blue phosphorescent device, we realized a 10 times lifetime improvement So this is, you know, the conditions are kind of not so important. These are running very bright. This is to 80% of its initial lifetime. This is the luminance curves. And you can see with our stack graded device, we get out to 620 hours at under these conditions, which are more aggressive than you'd use in a display, compared to 50 hours. So this was a big improvement. So we thought it's not good enough, not nearly good enough for displays or lighting. So let's try to deal with this problem at its source. That is, can we think of a way of getting rid of that excess energy before it does any damage whatsoever? So these are called Jablonski diagrams, by the way. This is the ground state of the triplet material. Might be the host or the dopant, we don't know. This is the first triplet state. And what these things are, they represent excitons, or excited state. So what you usually want to have is the exciton recombines and you get your blue photon out. That's wonderful. That's how basically God intended this thing to work, as far as I can tell. Okay, but now let's take two excitons in nearby molecules and they collide. That's these two guys. This is the Auger process. One goes up, but it's non-radiative. Okay, so we don't get the photon out. We lose 50% of our quantum efficiency. But one goes up to this really high excited state, very high up. And then it just comes back down. Nothing, no big deal, and we get our blue photon back. But once in a while, bad things happen to good molecules. And you get into a dissociative state, and this thing breaks up. So let's put in a second molecule over here, which we'll call a manager. And its triplet state is above this triplet state. And they're all in close contact. So our idea was, let's take that hot, excited state and bring it over to the manager, which will toss it back over here, and we get our blue photon back. That's a very kind of simple concept, really hard to realize, but nevertheless, once in a while, of course, bad things happen to good manager molecules, and it dissociates, but it's sacrificial anyway, so we won't care about that. So this was an idea to simply get rid of that, to manage that excited state so it wouldn't do any damage. So what are the requirements? We needed an intermediate energy between the hot state and the lowest triplet, so we needed something here so that it would couple this way. We needed it to be stable, so this didn't happen too often. And this had to be very, very fast. It had to happen faster than this thing. And we didn't have a lot of molecules. We had that very pretty blue molecule, which has a very high energy compared to our usual blues. So we used that for the manager. Not to get into any particular detail, but we made this is also something you can do in organic electronics. You can make your devices quickly. You don't have to go to LNF for 3 weeks to process the devices. You can do them all pretty much in a day. And we have a rule in my laboratory, which is your first result is always your best. And then it only goes downhill from there. I don't know if you've noticed that. But what we... So what we did is we did one device, M0, where so this is our graded device. This is our blue dopant. Our manager molecule is this carbene. We put the material uniformly across the emission zone. Then we just decided, well, maybe we should just put it where the excitons are most dense. So we made a series of devices, M1 through M5, where we just had these 10 nanometer slabs and looked at their lifetime as well. Now you have to have a lot of technology because you have to be able to package these things, you have to have clean molecules and so on. But if you look at M3 here, and this is a conventional device. It has LT90, which means it's lost 10% of its luminance in this amount of time. So if you take a conventional device with that phosphor in it, it's 30 hours. If you grade it, that's the Zhang process, you get 50 hours. Remember, it was about 60 hours, I think, in his first data. But when you put in M3, and you can put it elsewhere, but this is the best, you get 5 times longer, 140 hours compared to this one, and 30 hours compared to the graded device. So we've made another substantial step. Still not good enough, but it's getting there. This is T80, and you can see that it lasts longer, of course, because you've lost another 10%. You've allowed yourself to lose another 10% of your luminance. And these numbers come down because the manager is getting used up. So how good does it have to be? Well, for a display, LT95 is as much as you can tolerate. Okay, you can only lose 5% of the luminance of a color before you throw out the display. For a lighting, it's 30%, so LT70. So this actually is almost good enough for lighting. I'm not going to get into this, but we've now started to try to couple the chemistry directly with the physics model. That is, can we identify certain products that blow up, molecules that blow up with a certain energy level, and can we put that back in our model and get exactly the performance that we see, for example, in voltage rise or luminance. And so this is, again, our host MCP. This just shows the time of flight mass spectra of the clean material, and there it is sitting at 484, a mass of 484. And then if you run it for a while, you get all these other peaks, and we just kind of make this stuff up on the fly. These are the type of molecules that you might, or products that you might assume are coming out of this. And we've looked at all of the molecules. What the vision is that we now go to some really clever chemist and say, make us some of this stuff. And we'll just kind of sprinkle it in there and see if that results in a loss that we see. But where does it all go? So this is the most recent result. We've taken these managed devices and we've made white lighting out of them. They're super bright. This is for lighting, so it's funded by the Department of Energy. They're running, each one of these little pixels is running at 200,000 candelas per meter squared, or 200,000 nits. Your display in front of you is running at 100 nits, so this is 2,000 times larger in luminance. It's pretty efficient, not hugely efficient compared to what you might be able to get, about 50 lumens per watt. 10 times more than an incandescent bulb, about half as good as an LED today that you buy. Very good, beautiful color color rendering index of 89. You want it to be 100, but 90 is really a sweet spot. And here you can see it gives you very good, if you believe this photograph, and photograph is not data, but it kind of gives you a representation. You can see the real colors. You can even see the deep blue of this water bottle over here. And I guess it helps, is the point. We're getting, right now, the lifetime of these devices starting at 1,000 nits, which is closer to what your light bulbs are working at, about 80,000 hours. This is with blue in it. These are really complicated devices, but hopefully they're giving some reason to really start pursuing and moving lighting into all phosphorescence instead of fluorophore plus phosphorescent red and green. At 3,000 nits, it's about 14,000 hours. Okay, so in the last few minutes, I want to talk about solar cells, because this has also gotten extremely exciting. It's gone through kind of periods of misery and euphoria. It's a very manic, depressive field, as far as I can tell. Right now, the efficiency, current state of the art, is actually 15%. I'll show you some results that we got this weekend. Reliability looks like it's greater than 10 years, maybe up to 20. And cost, well, we don't really know, except that we have this faith-based science going on where we're using low-cost materials and low-cost processes and so on. So the hope is that eventually this will turn out to be low cost. That has not particularly been the experience, however, with OLEDs. OLEDs still remain more expensive than liquid crystal displays. People buy them because they're better, but but the cost is still somewhat of a barrier there. And of course, lighting, it's become a huge barrier. So just to put everything on, to level set everything, a single junction cell has a power conversion efficiency of 31%, which is, on a nice bright sunny day, here, even here in Michigan, we get 1 kilowatt per meter squared. There is plenty of energy to go around. So 31% means if you take a meter square of an ideal thermodynamically limited material, you'll get 310 watts out of it. Multi-junction cells, actually, I think this is behind the times. This is probably 44% today. Is it 46? Yeah, it's gotten up there. I'll change that, I promise. I'm not trying to make it look closer to organics. We'll never get there. All right, let's just be honest. Silicon solar cells are around 24%. They don't have the ideal band gap, but everything else about them is pretty ideal. Well, it isn't. They're very non-radiative materials, and you need a good radiative material to have a good solar cell. Usually when silicon is installed, it's somewhere between 16 and 18%. Gallium arsenide single junction cells have the record of around 29%, very, very close to the thermodynamic limit. And then probably, if you're anything like the Department of Energy, your hair is on fire because you have perovskite cells, and they just seem like they're the answer to everybody's dream. And then pulling up the rear is organic solar cells, but presumably they're cheap. So just a really quick view graph on how they work. They're basically OLEDs run in reverse, if only life were that simple. You take in a photon, you create an excited state or exciton. It drifts toward a junction, which is between a donor and acceptor molecule, so there are two layers. The electron finds the lowest unoccupied molecular orbital of the acceptor, and it dissociates from the hole. So the hole gets swept out this way, and the electron gets swept out this way. And this is, of course, a 4-step process, and 4 steps, each with an efficiency less than 1, in the end is a recipe for low efficiency, except that without going into details, working on the nanostructure of this, people have moved right up the line. So this is a timeline of the development of OPVs. Eventually, it started somewhere in here with the bilayer organic solar cell of Tang, which I've already talked about. And then good things happened along the way. This is our number here, but we think within a year or two, it will be up to above 17%, really pushing on it. And the attraction is to have transparency as well as efficiency. So when you think about what has been the limitation of, there's lots of things that have limited organic solar cells. But there's no question in my mind, the thing that's really paced that growth and efficiency has been the acceptor molecule. And the Tang device, he came out with this in 1986, remember 85, I can't remember, 85. He came out with basically parallenes, these 5-ring polyaromatic hydrocarbons, and he got 1% with his Kodak projector. Carousel projector was his light source. And he got 1%, and people slaved away and toiled away and toiled away and got to 2000 at 1%. Okay, then I had another good student. I've had lots of them. Peter Pumans put a fullerene in as the acceptor, and bang, we were right up at 3%, and within 6 months later, we were at 5%. And people toiled away and toiled away and toiled away, and they got to around 10%. And then it flattened, and it's not going nowhere. And then recently, there have been developments in what are called non-fullerene acceptors, and that has created a new line. And I think this one will get to the thermodynamic limit. And then you put them in tandem cells, and they get higher. So this is work coming out of our lab. Young-Shi Lee is my postdoc who's really doing this with Amy Chi in my lab. And these are non-fullerene acceptors. They're in a motif of in the molecule itself, an acceptor, a donor, and an acceptor. And this separates the electron and hole distributions across the molecule, reduces its binding energy, so you don't have such big energy losses. And you can make these things, what's really cool about them is they have very narrow absorption spectra. So you can make a device that absorbs completely in the infrared and is completely transparent. And it turns out that most of the energy anyway is being generated in the near infrared by the sun. You might not recognize this, but it's mostly NIR light that we have around us. And so he's been making devices. This shows one of these such devices. This probably may look familiar to you. I don't know where it is. But the transmittance of 30, 40, 50%. When you don't have a transmissive, it's about 11% efficiency, just a single cell. And now if you put it in a tandem, you have to do some optical engineering. We can make these things kind of as deep as we want, but we're now dealing with just tandems. We've done 4 subcells before, so you take out different slices of the spectrum, and you absorb in different slices in different cells, and with a tandem, we're getting 15%. So with that, I will conclude. I've taken you rather a lengthy tour through OLEDs and a perhaps shorter, but we're now in a kind of really exciting period of discovery in organic photovoltaics again. Organics present definitely new opportunities, many, many new opportunities in optoelectronics, but many challenges remain. On the other hand, against those challenges, we have large area, ultra-efficient color, tunability, architecturally adaptable form factors. You've seen some of those things, flexible, put them on roofs, put them on windows. Make organics too good to miss. Many technologies developed in this field will find new applications in all kinds of things, and we're already finding them in the Internet of Things, in medicine. There's a fellow from the University of Tokyo, Professor Takeo Sumeya, who now makes transistor circuits on films that are 1 micron thick. And you put them on your skin, and they go into every little fold and wrinkle that you have. And he can do sensing. It's really phenomenal. It's all organic. And of course, the human-machine interface, which is, for me, displays, lighting, et cetera. But there are challenges. Blue PHOLEDs need to achieve at least another factor of 100. So don't let anybody tell you this is an easy problem and it's done. It isn't. I had to be a little bit outrageous. So I just said, OPVs will bury perovskites in the near future. I'm from the Khrushchev generation where he banged his shoe on the table and said, we will bury you. So I thought I'd do that to perovskites, at least in this audience. Don't repeat anything I said. Oh, gosh, I would have taken it out then. Semi-transparency and high efficiency go hand in hand. We have designs now where we think we can get 20% efficient, 50%, maybe 60% transparent windows out of organics. We don't know of any other technology that can do that. Long lifetime is being achieved in OPVs. And patterning on large surfaces at low cost is driven by the display industry, but even there's lots of research, and we've built a roll-to-roll system in my own lab. So with that, I really owe everything to my students, and if I put the whole list up of those who have contributed, it would be several view graphs long. So I just decided I'd take a picture of my group and post it up here. So this is almost the current group. There's always changes in and out in the university group. The guys who have done a lot of the heavy lifting on the OPVs is Quinn over here, Amy, Young Shi, where is he? There he is. And then the OLED guys are Caleb and Chung Young. Let's see, who else over there? I'll find them. Oh, Xiao, Yue, et cetera. But everybody contributes in my group quite heavily. And of course, Mark Thompson in his group at USC My constant funding sponsor over the years has been Air Force Office of Scientific Research. If any of you go into academia, you will never forget the first call you get from an agency when somebody says, I'm going to fund your work, and that was AFOSR back when I was a wee lad, and Department of Energy and Universal Display Corporation. Thanks.